This is the solution to chapter 12, video segment 2. This question states, the rate of bacterial hydrolysis in fish muscle, the main mechanism of fish muscle decomposition, makes fish go stinky, is twice as great at 2.2 degrees Celsius than it is at negative 1.1 degrees Celsius. Estimate an activation energy for this reaction, and is there any relation of this answer to the problem of storing fish for food? So, using the 2-point Arrhenius equation, we can, it gives us two temperatures and it gives us a proportion twice as fast. So if we use the 2-point form of the Arrhenius equation and solve for activation energy, we can estimate what it's looking for. So this is the 2-point form, natural log of K1 over K2 equals negative activation energy over R times the inverse of temperature 1 minus temperature 2. So just kind of rearranging, multiply by R, right, get this over here, then we can divide by negative 1 over T1 minus 1 over T2. That isolates energy of activation. So energy of activation equals negative R, natural log of K1 over K2 over the inverse of temperature 1 minus the inverse of temperature 2. Now plugging in our values, for R, of course, we have the universal gas constant, 8.314 joules per Kelvin mole, times, so it says that it's twice as fast at 2.2 as it is at minus 1.1. So if the rate is twice as fast, because it's just like a generic rate law, because the rate is twice as fast, the proportion of the rate to the rate constant is like 1 to 1, well, not 1 to 1, but yeah, I mean, if you double the rate, you're going to be doubling the rate constant, right? Because the concentration isn't changing. So basically, we know that if the rate is twice as fast from 2 to 1, then the rate constant is going to be twice as fast as well. So we got natural log of K1 over K2 is natural log of 1 over 2. Now divide all that by the temperatures we have, convert these to Kelvin, we got 2.2 plus 273.15 minus 1.1 plus 273.15 gives us these values for Kelvin, temperature, absolute temperature. So, for temperature 1, we've got 1 over 275.35 Kelvin, which is the 2.2 Celsius, minus temperature 2, 1 over 272.05 Kelvin, which is the minus 1.1 degrees Celsius. So when you plug this in the calculator and solve for it, we get 130,000 joules per mole, or 130 kilojoules per mole. So this is a relatively high energy of activation. And so that kind of leads into the second half of the question, which states, is there any relation to this answer to the problem of storing fish for food? And the answer is yes. I mean, already we can see there's got to be something, right? Because you go up 3 degrees and the rate doubles, which isn't really typical for, well, I shouldn't say it's not typical, but it's just that's not a lot of temperature change for the amount of rate change that you're seeing. So there's obviously an explanation for this, and the explanation can be found with, of course, the Arrhenius equation as well, just a different form. The linear form of this equation states that the natural log of K is equal to the negative energy of activation over R times the inverse of temperature plus the natural log of the frequency coefficient, I think it's called. This is irrelevant for our purposes right now. So if you were to graph a graph of a reaction, a rate that is has a low energy of activation, you would expect the slope of the line to be small, right? If this number is not very big, divided by R, it's not going to be a very large value, so you'll have a low slope. Now, if energy of activation is really high, such as 130,000 joules per mole, the slope is going to be very steep. So this is low energy of activation slope. This is high energy of activation. And so, as we can see, if you're going to change the temperature on this one, let's say, this much, you're only increasing that much, right? Not very much. But if you change this one by the same amount, you're increasing by that, right? A line that's much greater than that. And of course, natural log of K is going to be proportionate to the rate as well. We kind of already talked about that here. So just looking at the graph of the equation here, if you're going to change the temperature in a reaction with a high activation energy, that's going to change the rate a lot more dramatically than if you're going to change the temperature by the same amount in a reaction with a low energy of activation. So that's looking at it mathematically, and then just conceptually thinking about it as well makes sense, right? For this reaction to get over the hump, right? The activation energy hump. If the energy of activation is low, if it's a small hump, most of the molecules are probably already there, able to do it, right? Let's say like 80% can already do it. This one, right? We got a high hump here, energy of activation. So maybe only 2% of the molecules can already do it. So if you increase, this one by 2% more, increase the temperature, 2% more of the molecules can go over the hump. That's really hardly even a noticeable difference. But if you increase the temperature, 2% more of these molecules can get over the hump, right? You just doubled the rate, right? You just double the number of molecules that can get over the hump. And so that's kind of a way to think about it conceptually as well, that not very many can get over this hump when the activation energy is really high. So a temperature change, even increasing the number of molecules by a small amount, is going to be proportionally much greater rate change than the same number of molecules getting over the smaller hump, because more can already do it. So I guess that's kind of why we see what we see here, because the energy of activation for this fish, hydrolysis, is so high. You really have to get it cold, because temperature has a really strong effect on the rate of this reaction happening. So the colder the better, right? As we can see, 3 degrees changed a lot. So that's kind of how this relates to the problem of storing fish for food.